My name is Alexis. I work at Airbnb for 2 years now on the infrastructure team, and I'm going to be talking with Krishna tonight.
Oh, hey, I'm Krishna. I'm in the data infrastructure team in Airbnb. I've been there for a little under 2 years now.
Yeah. So we have 25 minutes to tell you about Kafka at Airbnb. Typically, Kafka, anything Kafka related means Jitney, and that's the name of our project that we're going to present about tonight. There's a lot of stuff, and it's always hard to find the right technical level for this kind of audience. So feel free to ask questions as we go if we need to go deeper or if it's too high level. So first, a few technicalities. So what is Jitney? Jitney is a bus we used to have down at the office around Airbnb, and it's actually, if you talk about a Jitney, it's actually a bus carrying passengers. So it was kind of a good fit for our use case, and the look of that bus was an inside joke. Just to give you a scale of Kafka usage at Airbnb, it's definitely smaller than the linking numbers, but we have one production cluster. We use the 8.2 version. We have about 90 brokers. I describe them as small because we try to have not to have too much data per brokers, basically. We have 70 topics. We use replication factor 3, and that's 5 billion events a day. Not a trillion yet. Inbound, it's 80 megabytes per second, and outbound, it's 1.5 gigabytes per second. So there's a big unbalance here. And we are typically network bound, which also explains the number of brokers we have. In terms of operation, it's been actually very stable over the last 2 years. Kafka has been one of the most stable components of our infrastructure. So that's kind of the technical aspect. So why did we create Jitney at Airbnb? If you pick any metric at Airbnb, it's most likely looking like this. Everything doubles every year. Data is actually growing even faster. That's true for the number of developers, number of services we have, amount of data, number of message type flying around. So you have a huge proliferation of Kafka producers and Kafka consumers. We actually encourage people to use Kafka to decouple services. So at the end of the day, we had a situation where the way Kafka was used was never the same between two use cases, and there was a huge need to standardize everything related to Kafka. So the goal was really to go from a place where everything looks the same, but it's not the same, and it's most likely broken, to the 4T approach where we enforce best practices, we enforce patterns, we provide delivery guarantee, and so on. So really standardization. What are the use cases we wanted to address with Jitney? We had 2 main use cases. The first one is about the classic message bus use case, and it's kind of where my team, production infrastructure, was coming from. We were pushing people to write code outside of the big monorail application and create more services. So we needed a way for these online services to communicate asynchronously and to publish events that might be consumed by unknown consumers. So in these cases, we want standardized events. We want to enforce at least once delivery, and we want to provide standard clients for Java and Ruby, which are kind of the 2 main languages we have at Airbnb. And obviously, we also wanted conventions over configuration. I'll go in more details later. The other use case is the data infrastructure use case.
Right. So user activity logging and making sure all the activity that happens on the site, we collect the data and put it in the warehouse. That's the main use case here. And this is one of the biggest driving use case for Kafka. So this is one of the key things that the data infrastructure team does. So The user activity includes a number of things, like information like how much time it took to load the site, the images, if there are any exceptions or any information we need for improving the application. We want to get that back. We want to keep track of how many searches happen, how many requests came in, bookings happen, and fire events for each of these things. And these things feed into many of the key business metrics. And another big use case is for experimentation. When a user logs in, the user gets assigned to various experiments, so we need to keep track of which user got assigned to what experiment and what was the result of that. So all of that comes through Kafka to the warehouse. So this event data is extremely critical for building a lot of the data products, including business metrics, and also curate the data, take some insights from the data, and take it back to the product and improve the product. So because it's so widely used, it has so many different applications, we wanted the data ingestion pipeline overall to be reliable, like as in timely and complete. So some of the challenges we faced in achieving this high reliability are the following. So 1.5, almost 2 years ago, we used to have all data coming in JSON format. So this has no schema, so the producer can go change the schema, add fields, remove fields, rename them. So that led to a lot of problems. One of the main problems that we had was producer side changes breaking the downstream consumers. So you go remove an important field, or the producer mistakenly forgets to log an important field, then the data sometimes even becomes useless. So this was a pretty common incident. Source of incidents. Then the other challenge we had is we had like hundreds of events, more than 800 event types, but because of various reasons, they all ended up in a single Kafka topic, which was becoming a problem because now if you want to scan something, you have to read a lot of data from Kafka, so that was becoming a limiting factor as well. And some of the other problems that Alexi already hinted to, like we had proliferation of various producers. They had different configs, improper configs. So producer going down and data loss was common. And again, related to that, lack of monitoring on the producer side led to a lot of data outages, and we discovered them several hours or days later, which was a big problem. So all of this led to too many data outages, and these kinds of incidents kind of eroded the trust that people had on the whole ingestion pipeline. So from our team, we wanted to solve this problem in a reasonable, reusable way. So just to give you some examples, like a year ago, a little over a year and a half ago, so data outage was so common that some of these applications, like the CEO dashboard, they were super unreliable. And at one point, we had a whiteboard next to our team where we used to track the number of days since previous incident. It used to be in single digit for several months. And at one point, our experimentation platform kind of produced unreliable results, and one of the product managers has to send this email saying, "Don't trust the data in our experimentation." It was this bad. So that's where our teams together started to come up with a plan to address these problems.
Yeah, and so in both cases, we can actually find a lot of shared needs, especially around schema, for example. So what are the components of Jitney if we start looking at the implementation? The first one is a schema repository. So we actually implemented, when I say repository, it's actually a simple code repository or Git repository. We use Thrift schemas, so we expect basically every event to be declared in a Thrift file. We decided for Thrift from a few reasons. One is that the syntax itself is at the right level for most people, and it's actually also pretty simple. If you think about events, many people need access to that information. We have the data scientist that might need to design a new event type. We have a product manager as well, or a developer. So you kind of have a different set of skills. Not everyone knows how to write some code. So Thrift, the idea was Thrift language was at the right level for that. Like we said before, we needed a good solution for Ruby as well, so we did a bunch of benchmark for the different schema technology, Protobuf, Thrift, Avro, and Thrift actually had the best serialization performance in Ruby. And also Thrift is widely adopted. It's easy to find Thrift bindings for your language. So we were kind of thinking ahead of the JavaScript use case and things like that. So the main advantages of a schema repository is to bring everyone in one place for review and collaboration and documentation. In terms of technicalities, so the Thrift repo is part of a typical CI pipeline and publishes version jars and version gems that will be used in the applications. One question that you might get from your developers is like, why do I need schemas when JSON is so easy for me to use? And many people might actually hate you initially for that, but actually in our experience, the adoption has been pretty successful, and people actually like having generated classes that they don't have to maintain, or and it's actually a good thing for developers. I want to focus a little bit on one specific work that we did in the schema repository. So we wanted a way to manage schema evolution. So in the Thrift schema, we have a convention that every event will have a known field describing the schema associated with that event and what version of the schema is actually used. And we use a typical semantic versioning for the schema, so that will allow us to track breaking changes or backward compatible changes and so on. And all of that is carefully documented. It's part of the review process. If you do a change on the schema, we're going to change the version accordingly. We're going to give you recommendations on how to propagate these new versions across the infrastructure. From a consumer perspective, it's actually very, very convenient, because now you can easily implement a consumer that will deal with version 1 of a schema and version 2 of a schema. So it's being explicit is actually super helpful here. So a quick example of a Thrift event. So that's what it would look like. The interesting bits is the schema field, like I mentioned. So it's a namespace plus a version. That namespace allows us to infer the class name that we need to use to deserialize the Thrift event. So yeah. In addition to the schema repository, we created a topic repository. So one thing we found out in many cases as well is that two producers might publish data to the same topic, but they might use different partitioning function, and the ordering is then different from the consumer. Something we wanted to avoid as well is having kind of a whitelist for anyone to dump any kind of data on a given topic. So the topic repository is one place where we expect all topics to be declared, and for that topic we're going to aggregate the characteristic of that topic. So the name, obviously, but also the ordering specificities of that topic. And we do that through code. So basically you can say, here is my new topic. I'm going to use this specific function to do the partitioning of the data. And we actually whitelist the schemas that are allowed on that topic. And once again, it's great for communication, because by nature, the use cases are highly decoupled. You don't know who emitted that message. And having one central place where everybody can go and get the information is super valuable. It's also makes your code more dry, because we can unit test the partitioning function. We can do a bunch of stuff with that. So right now the topic repo is defined as a simple Java class. I think we could easily use higher level DSL, I would say, but the Java class has been actually working nice so far. So, like I said, you describe the whitelist of accepted schemas. You define the key provider is the partitioning function. The third piece of the Jitney project is the clients aspect. So if you ask two developers to use a Kafka client, they're going to do it differently, and most likely both of them will be wrong, especially on the consumer side. So the Kafka clients are actually really hard to use correctly. It was specifically true with the 0.8 version. 0.9 is definitely better. But still, in terms of commit management, no two developers will implement the commit offset in the same way. So we had no clue if we could actually claim to be at least once delivery, and this was a big challenge for us. So same thing for configuration. What is the right time-out value? What is the right batch size for the cluster we have? What about monitoring? Monitoring change in every version of Kafka. There's no standard way of reporting your metrics to StatsD or that we use. So we needed a way to factor all of these aspects in one client. So obviously the Jitney client provides the standard monitoring. We have a StatsD reporter that you can use with up to the 0.8 version. We have an easy way to plug your client against a cluster without having to repeat the seed brokers and the zookeeper configuration. And where it becomes powerful is when you tie your client implementation with the topic repository and with the schema repository, because you can make a nice integration here. Specifically in terms of consumer, so I mentioned managing the offset commits. The Jitney client will manage the threading for the developers. As a developer, you just give me one function that I'm supposed to call for a given message, and behind the scene, the Jitney client will deal with the threading properly, making sure there's no in-flight messages when we commit to zookeeper. And a nice thing as well that we can build on top of the Thrift classes is a way to do the message dispatching to the function handlers using actually the classes. So we have kind of a polymorphic dispatching that make the consumer code simpler. I'll go briefly through a code example. So that's a producer. We use the Google Guava services as an abstraction to manage the state of the producer. So in that case, we simply configure a producer. You just provide a client ID. We assume the Kafka cluster is local in that case, and from there we build. We have conventions to infer zookeeper hostname and so on. You define what topic you want to produce to, and then you just publish using the canary event. In that case, is a Thrift class that you define in the schema repository. The Java consumer. So like I said, you need to say for this canary event class, I want this function to be invoked. So the dispatcher will let you express this, and then you create a consumer saying subscribe to this topic, use the dispatcher, and as soon as you start the consumer, there's a bunch of threads that actually similar to the Kafka streams that will invoke the handler functions. Briefly, the one more piece in the Jitney project is the proxy. So we have an HTTP proxy that allow mobile applications or web browsers to send us events. We accept the binary Thrift or the JSON Thrift protocols. And it's also part of the Ruby solution. So the Ruby client is just a client to the proxy to publish or consume messages. One last piece is Krishna's piece.
Yeah, so I'll talk about the warehouse integration. So we talked about the schema registry, which generates a jar with all the schemas and topics. Producers use that to produce the data. Now, how do we actually consume it into the warehouse? So this is a rough summary. So our stack, we have Jitney producers, and then we have a Spark streaming job, which runs every minute and consumes the micro batches. So Spark streaming, we use 1.5, which has Kafka Direct Connect, and we do 1-minute batching. So one of the issues we ran into in this is checkpointing. It used to be quite unreliable. Sometimes it used to take more than a minute to just checkpoint, and it was delaying all the batches. So one of the things we did was to write a separate custom checkpointing class, which commits the offsets to HBase. And then we read the offsets off of HBase every micro batch, do the diff, and then consume the range of offsets in each executor. So we use HBase as a state store. This is where we store all your metadata as well as data. And then periodically, we take the data out of HBase and dump it into HDFS and create a Hive partition for that. A consumer can query the query Hive. We mount the current partition in HBase, also in Hive. So a consumer can query past partitions, hourly or daily partitions in the past, as well as the current hours data through the current partition in Hive, and then they combine the results. So the interesting thing is that the schema is going to be the same, so you can easily do a union all across these different partitions. We're also working on a Presto connector, so users can query through Presto also. This is a rough diagram of how it looks. We have various producers. Java, mobile, and JavaScript producers go through the proxy, and data in Kafka is consumed by the Spark streaming pipeline. And then we use HBase for state store. And then Hive queries combine past and current partitions, just like I described. And the Spark streaming job basically consumes the Jitney jar. Anytime there is a newer version of the jar, the job restarts and picks up the newer version of the jar. So you can always have the same schema that is used on the producer nearly. So this is pretty good in terms of timeliness. So the other challenge I talked about before is completeness. So if producers produce, say, 100 events, how can we be sure that all the 100 events actually make it to the warehouse? So that was a big challenge that we wanted to address. So we wanted to provide an SLA where we can look at a dashboard and say, okay, we produce 100 events, and these are the number of events that actually landed. And if some events are lost, we want to be able to say, okay, where did they actually get lost? So to address that, we built something called an audit pipeline. So inside Jitney, in the producer, we emit some additional metadata with every message that we send. At a high level, you can think of it as the following. Every producer has a unique ID, and then it stamps a sequence number with every message that is sent. So for example, the Ruby producer produced 4 messages, and somehow one of them got lost. In the warehouse, we can do a group by on the process ID or the producer ID, look at the count of the messages and see the min and the max sequence number in a given hour. And by doing a diff, we can compute exactly how many messages are lost. So this is how the metadata looks like. So important point is the ID field, which is the process ID or the producer ID. And then there's a value, which is an incrementing sequence number. And in addition to that, we also include information about the actual bytes sent. So we can even say what was the size of the message that was lost. So this is good for tracking how many messages were lost. So now how do we track where the messages got lost? So for example, in this example here, the producer may lose the message, or some intermediate step may lose the message. To solve that, we extend the same metadata we have into an array. We call it tiers. So here, this thing is an array you can see here. What we do is, at every tier, we stamp the same set of metadata and add it to this array. So this is part of Jitney. So all the producers that use the jar will get all of this for free. And currently, we have 2 tiers, the producer tier and then Jitney proxy tier, which is a gateway for a lot of the web messages that we get from many browsers and mobile, and also a lot of the messages that we produce from Ruby producers. So we can track at which tier the messages got lost as well. So now, let me quickly talk about how Jitney is used, what are the different use cases, quickly summarize and conclude. So we have a bunch of use cases. Like I've listed 5 important ones here. User activity ingestion, the one I just talked about, is one of the main contributor of a lot of the data. So the second use case is ingestion of database changes. We have built a system which listens to the MySQL bin logs and emits messages into Kafka. And we use the same pipeline that I described before to consume both facts and dimensions. And the same pipeline generates both facts and dimensions into the warehouse. Finally, so the third use case is a pub/sub use case. The web backends generate control events, which is consumed by various payment processors. That's the payment processing use case. We use experimentation, produces a lot of events, like it contributes 30% of our overall traffic. That's another big use case. And then we use it for cache invalidation in our Memcache and Redis clusters.
Many services from trust and safety as well rely on that. So typically, any kind of background checks could be done offline, and the Jitney standard events emitted from our web tier are actually used by these services to kick off like asynchronous processing.
So to conclude, the main takeaways main lessons that we learned over the last couple of years is having a standardized way of having producers and consumers, having proper monitoring and reasonable configs, and a very simple way for producers to generate and send messages. That eliminated so many potential incidents that could have happened. That simplified our developers' lives significantly. And along the same lines, having proper schemas so the producers and consumers can talk and figure out exactly what should be in the schema, that helps a lot. A simple way, a single place to go and look at the events. And 2, audit pipeline has helped us a lot. Like at the end of each day, we get a report saying how many messages were lost, and it's usually in the order of like a few thousand out of 5 billion, which is really great. To quantify what exactly our SLA is. And these basic foundational pieces have been a huge advantage for us in building new services, moving fast, and in general, as we have more people, for them to communicate and figure out what the event schema should be or what the event does. So we can take some questions.
Questions? So the question was, what is the difference with the HTTP proxy we mentioned here and the Confluent petition? Yeah, I think it came around at the same time. I think one main difference is that we don't have a consumer in the HTTP proxy, and we don't expect Avro schema. It's slightly more also than an HTTP proxy. We actually have from the web application, when we emit user activity events, we don't want any kind of back pressure into the application. So the link between the Rails process and the proxy is actually over local UDP. We run the proxy locally on the machine. The Rails process emits over a UDP socket to the proxy. So that UDP endpoint is embedded in the proxy as well. The main goal was to not having anything that could take down the site in case of issues with Kafka. That's the case we had in the past. So we use UDP as our short circuit, basically.
Hi. What was your requirement to use Spark streaming to get data of Kafka into HDFS Hive rather than using Camu?
We used to use Camu in the past. We used to run it like every 30 minutes. Spark streaming is making it more real time. We have data landing much faster, like less than a minute. We dump to HDFS at the end of every hour. So the current hour is in HBase. When you query from Hive, it goes to HBase. The current hour query goes to HBase. We have connector from Hive to HBase.
I'm just curious, do you still need Jitney if suppose you use Cassandra? Cassandra in working with Spark and Kafka, a slightly different kind of technology stack. What's your take on that? I don't think a lot of efforts, suppose you use Cassandra, situation will be totally different.
Cassandra for the state store?
To store data?
Real-time insertion, he said.
Right. So Jitney, it's kind of complementary. So Jitney is adding all of these.
So Jitney gives you the schema piece for the.
Yeah.
I'm not aware of the Cassandra solution.
Sure, but you still need to get schemas from somewhere, and that's where Jitney comes into picture in our case.
Okay, we can. They're with Airbnb.
Okay.
Yes, can you please give some details about how you address the monitoring challenge that you mentioned?
Yeah, so we use Kafka 8.2, which has a way of letting you plug in a custom reporter. So we have a StatsD reporter. It's open source on GitHub, so you basically, by default, every producer, every consumer, brokers as well will use that reporter, and we'll send metric to a local StatsD server. So we did some effort to tag properly the metrics. I know that was some work on this as well. So we have a StatsD reporter.
Could you also elaborate on the scenarios when you lost messages and how did you find them and how did you make sure it won't happen?
So we typically lose messages when we from the web tier that actually use the UDP socket, and so you see two cases of loss. Like one is when you have a burst of messages, and the other is when you have a big message. So you might lose one big message over that connection, or if you have a burst of, let's say, many small messages, you might lose some as well. And that's why in the auditing data we track counts and also size, because we want to be able to say, okay, we lost some messages because they were big, or because we had a burst of messages.
Okay, one more question.
Can you give more details about what's your consideration? Why do you want to put a proxy between Kafka and the producer instead of like directly pushing into
Yeah,
Kafka?
so the slide was slightly wrong. Java talks directly to Kafka. The proxy is only used by components outside of our infrastructure, so mobile applications or the web browser will talk to the proxy over HTTP. The Java talks directly to Kafka. It's like it's a standard way of doing things. On the Ruby side, we use that proxy because it was actually easy to leverage that proxy and just have a simple Ruby client against these interfaces. Yeah.
Okay, we'll do one more.
Thank you. I was interested in the tires, the tracing tires you were specifying in the slide. So if it doesn't reach Kafka at all, these are lost in the log messages, is it?
Yes. So if it doesn't reach messages at all, the sequence number is incrementing, right? So you can do a min and max and look at the count, and then the difference is really how much you lost.
No, what I'm asking is if this event does not reach Kafka.
If you send only one event, yeah, we might not see it.
Correct.
But
yeah,
in at the edges, you have boundary conditions, yes. But in the case where you have constant stream of data, we can actually detect them. And in that case, the canary event is actually producers that we run as part of our monitoring solution. So we have canary services that emit events at a known rate to constantly monitor.
Great. So we'll do more questions at the end of the entire meetup. But thank you guys.
Thank you.